The Travelling Salesman Problem. This is one of computer science's classic hard problems, and today we're gonna figure out just what is wrong with this salesman and how do we solve his problem. You're watching another episode of Graph Theory. Hello and welcome back to Graph Theory. Now, as a word of forewarning before we jump in, note that this episode will not have any pseudocode, and the reason for that is because we have quite a lot of content to come and I don't want to, overwhelm you with too much. So alright, with that out of the way, first and foremost, what is the Travelling Salesman Problem? Here's the deal. We have a salesman, and basically he wants to travel to a certain set of cities. However, the restriction is that he can only visit every city exactly once, and something needs to be minimized in, the choice of path that you actually give him, be it distance or travel time. How is this a graph problem? Well, every city is a vertex. At the same time, the quantity you want to minimize is actually the edge cost. This problem is usually formulated as an undirected weighted graph that can be complete. So how do we solve this problem? As it turns out, there is a simple naive solution as well as a more complex dynamic programming solution. Obviously, the dynamic programming solution is the better one of the two, but let's start simple by taking a look at the naive method. And that would just be to try every possible combination we can. The easiest way to do this is to actually use a recursive solution, so let's actually take a look at how this is done. Now, let's say we have a very simple graph that looks like this, and we want to find a Hamiltonian cycle. Obviously, if we want to start at A, it's going to look something like this. We're going to start at A, we're going to visit each one of these cities exactly once, and then we're going to end up back at A. So we know that what's going to vary is just the stuff in the middle. So our recursive solution actually tackles these three unknowns in the middle. When we actually call it over the scope, what's going to happen is, it's going to just vary one of the nodes in the path, and it's going to actually sort of delegate the rest of the work to another recursive call. So we're going to try B first, and we'll see, after this recursive call has finished, what kind of result we'll get. Then we'll try C. Once again, on this recursive call, we'll see what kind of results we get. And then we'll try D. And then once again, we'll actually see what results we get. And at the end of the day, we pick the best out of this tree. So don't worry if it's not too clear right now. Just understand that this is the rough idea of how we're going to approach this problem. And we're going to see more examples of this in action. To help us, we're going to use a little notation that looks something like this. What this basically means is I want to find a path that starts at node A. So we always start and end at node A, and that's fine. It doesn't actually, break our answer in any way. So we want to find a path that starts at node A. It ends at node X, which is what we actually write in here. And we have a set of nodes here, which actually tells us which nodes must be visited before we finish up at X. In case this isn't clear, let's look at a more concrete example. If I say this, what this means is I want to find a path that starts at node A, it ends at node A as well, and before it actually goes back to node A, it needs to visit B, C, and D, each one of them exactly once. Now, what this basically means is that if we were to go back to the graph just now, it means that we just want to solve the traveling salesman problem on this graph. Right? Recall what that statement means. We wanted to start at A, we wanted to end at A, and we wanted to visit everything else exactly once. So essentially, this just says solve the traveling salesman problem on that graph. So hopefully up to this point, everything is clear. With this, we can actually begin to trace the naive method of solving this problem. Okay, so let's begin with the actual trace itself. As mentioned, what this means is basically I want to solve the traveling salesman problem on that graph. Now, what's going to happen is, as we've described earlier, what this guy will do is it will actually try out one of the nodes. So notice that we've actually varied up the ending points. So this is basically that step we saw in an earlier slide, this part where we actually vary this last node. That is essentially what's happening here. We want to change up that last node, and basically everything else is just, everything else within the list. Of course, we'll have to remove the node that we will visit at the end because we don't want to double visit a node. So hopefully you get the idea. Basically what's going to happen is this call is going to make subsequent recursive calls that essentially do the same thing. It just takes out one of the items from this list, and as you can see, there are as many calls as there are items in this list. And the idea is we just want to try these out to see what works best. So what happens next? Well, these guys are going to make their own recursive calls, once again making a pick between the options that are available to them. What this means then is that each one of these will produce 2 more recursive calls. Notice that these are essentially just picking different permutations of which one to visit first and which one to visit at the end. At this point, since there is only one option left, each one of these will just generate one more call. And essentially that's it. This is our base case. If you notice what each unique path in this tree actually represents, you realize that, every path is one possible combination of visiting all the different cities. In fact, if we were to take this one step further, basically we want to go back to A at the end of the day. And what this means is now, every single path on screen is one possible Hamiltonian cycle. All that's left for us to do now is to find the best Hamiltonian cycle out of the lot. Now, how do we do that? Well, we look at a graph, we look at the edge costs, and we decide which one actually minimizes the cost. Whether you want to refer to the graph itself or actually express it in a way that is probably what a computer will actually work with, that's up to you. Of course, right now what we have is a symmetric matrix for the very simple reason that this is an undirected graph. But of course, having a directed graph does work as well. It does make sense in certain contexts as well. But I'm just saying that because we have just a simple undirected graph, this is going to be a little less exciting. But nonetheless, we will be seeing a complete picture of how these steps work. So anyway, applying the edge costs here, we can actually sort of stick them back into our tree. All the costs reflected here are just the distances between A and the last stop, whatever the last stop is. This of course allows us to accumulate the current distance we have so far, as well as the path we've taken so far. Once again, we query all the edge costs now between these pairs, and we'll push them up. Of course, we can't just return these values, we have to keep track of the distance we've traveled so far, and we've already traveled from A to this level in the tree, so we need to actually sum up the distances that have been incurred up to this point. So doing the summation, returning the results, that gives us a path that, has now extended to 2 nodes, as well as the accumulated distance up to this point. Hopefully there are no big surprises here, everything should be exactly as you would expect. We do the same once again. We find the distances, we sum them up with what we have so far, and we push them up. But there is something kind of interesting here. Notice that each one of these guys have actually spawned 2 recursive calls, and now we have 2 distances coming back. Well, this is where we can start to do our optimization. We have a path here, but it's longer than this path. What that means, of course, is that we can actually throw this out. Same deal for all of these. Essentially, we pick the shorter of the 2 paths, and we basically keep that as the best result we have so far. So we bubble the better results up, we keep the best path we have so far, and of course the next step is to do the same thing. Except now we are returning to the very root of our tree, and what this means is our trace is about to be complete. Once again, there are 3 distances, and coincidentally we have 2 that are equal. Of course, at the end of the day, we still have to make our pick, so it's up to you how you want to break this tie. I've decided to go for just, the smallest letter. But yeah, this basically gives us the result of the entire calculation. We've just looked at every possible set of paths, and then picked the best one out of the lot. The result of our computation, once we actually append it to A, gives us our closed Hamiltonian cycle. And we also know its distance, 19, is minimized. Now, why do we call this the naive algorithm? Well, let's see what happens when we use n cities, and let's take n to be, kind of a large number. Essentially what's going to happen is our first call at the very top is going to have a set of n-1 items. That of course makes sense because, well, you already have one item here, and you want to sort of test all the combinations of the remaining n-1 cities. What this then means is that we're going to generate n-1 recursive calls. Since we've already visited one out of the n-1 cities for each one of these will have to actually generate n-2 recursive calls. Do you see the problem yet? What we have here now are n-1 times n-2 instances, and each one needs to make n-3 more calls. This is going to add up very, very quickly. In fact, what we essentially have is growing powers as we go on, and what we get at the end of the day is essentially the factorial function. This is why the naive solution to the traveling salesman problem is in fact an O(n) factorial solution, which is extremely slow. Once n grows beyond, in fact, a small number like 4 or 5, this starts getting a little bit difficult to handle. Once you have, say, 20 cities, this is just impractical to do. And just to see the effects of the factorial growth, this still looks manageable, but all we have to do is add one more city to the mix, and the whole thing starts to look a little bit ugly. As you can imagine, the naive solution is just not practical. I mean, n factorial grows really, really fast, even for very small values of n. So yeah, you wouldn't want to run this on any moderately close to real-world data sets. However, thanks to the power of dynamic programming, well, we can find an optimization. This method we are about to talk about is called the Held-Karp algorithm, and yeah, it uses dynamic programming and a very interesting perspective to solve this problem. Now, we've talked about dynamic programming in the previous episode, so you may be quite tempted to actually look to see if there are any overlapping subproblems, but because this is an enumeration of all possible combinations, there necessarily isn't. Sure, I mean, if we were to look at the larger version with 5 cities, you may notice that certain things are repeated, but these are at the very leaves of the tree. There just isn't very much overlap, which means that it's not very easy for us to optimize. As it turns out, the reason why we are sort of stuck in this rut is because we are actually trying to generate all possible combinations from the top down. What that means is we sort of start from just one function call, and we're trying to use it to generate more and more function calls. When that's done, they just return and bubble their way back up, and what we get at the end of the day is a result after performing basically what is all the computation. Instead of doing this, let's actually turn the whole problem on its head, and actually look at this problem from the bottom up. Once again, this is our graph, and what we're going to do is we're going to start from the simplest function call. What is the simplest function call? Well, the function calls that actually are terminal. These are the ones that go straight to A and then finish up. So these are the simplest ones, we don't have to visit any other node. Now, let's go one level up in terms of complexity. What are the ways in which we can actually end up at B? Well, we could go through C, we could go through D. Notice that we're not talking about A here, because as always, we've fixed A to be the start and end of our path. So essentially, we can ignore it at this point. Of course, we are sort of bubbling down the distances as we go along. That's not too important at this point. Just make sure you're familiar with the thought process of generating all these function calls. Essentially, we are still enumerating all the possibilities, but we are looking at enumerating the function calls as opposed to all the possible paths. And you realize that, well, there are some optimizations we can do. But not at this point. At this point, we are still sort of doing all the hard work. That's not too interesting. Let's try and just move one step further. Now, actually, there isn't a whole lot we need to do. For example, once we've looked at B and C, really we're just left with D. So that leads to just one more function call for each one of these. But hang on a second. Do you see the overlapping subproblems? They are everywhere. What this means is, now, because we've just turned the whole problem on its head, we have actually made these overlapping subproblems just jump out at us. What that means, of course, is that, well, we don't want to do the double work. We just need to do it once, using the results that we have computed so far. What's really cool is because we've actually done things from the bottom up, we already have the results of all these function calls that are ready for us to use. So realistically, when we're looking at this, we don't have to generate a whole tree of function calls. We just need to reuse the results that was generated here, and that gives us the results here. In fact, all we have to do is to grab the results, perform our comparisons, and once again, we actually have the optimal results for each one of these function calls. Why is that important? Well, that feeds into our final function call, which just takes a look at the results from these three invocations, without having to think about what needs to be done here. Do you see the beauty of this? By just turning the whole problem on its head, now every single function call only needs to refer to a small number of function calls in the previous level, and that saves us a lot of trouble. The results that are generated at any point is then put into a memo table, memoization, dynamic programming technique, and in the next step, we just need to refer to the results we already have. We have now, by doing less work, still arrived at a good and correct answer. Now, in this case, we only have 4 cities, and the savings might not be that great. But when we actually look at a larger scale graph, for example, the one with 5 cities, you now realize that, hey, it's not too bad. Even though this kinda looks confusing, if we were to actually take away all the distracting elements in this image, you realize that, it's actually quite sparse. The number of operations we have to do isn't that great. Compare this to the original graph, just looked at how packed everything is, how much work we have to do. Well, there are some savings. Now, to analyze the time complexity of this particular approach, what we're going to need to do is we're going to have to actually sort of understand what's going on and then try to understand the math behind it. Recall that what we're trying to do here is enumeration, except instead of enumerating all possible paths, we want to enumerate all possible function calls, because we realize that there are actually less of those. Now, what is enumeration? Enumeration in math is generating a power set. What does that mean? Now, let's take an example here. Let's say we have a set S that contains the numbers 1, 2, and 3. Generating a power set out of set S implies actually going through and finding every possible combination of its elements. So, we indicate a power set by the symbol P, and essentially a power set of S includes the following. First, nothing. Right, that is one possible combination as well, in which you have none of the items selected. Of course, we could have any one of the items picked, so we can have 1, 2, or 3 as possible answers. We could also pick 2 items, and of course there are just 3 ways to do this. Finally, we can pick everything. And so, this is our power set. These are all the possible combinations of sets that we can generate out of these 3 numbers. So, essentially what we have are 3 items here that generate 8 possible sets at the end of the day. Now, those of you who are kind of familiar with your binary may see a pattern here. In fact, the size of a power set is 2 to a power of n, where n refers to the items in the original set. This is actually remarkably similar to when we have 3 binary digits and we want to find out how many combinations there are, because essentially this is the same problem. What we are doing is every possible combination that we can generate is like taking each item and switching it on or switching it off. What we're essentially doing is we're enumerating every possible combination in which we can actually switch the items on or off. But I guess we're kind of digressing a little. The big importance point here is that you should understand that the size of a power set is 2 to the power of n, where n are the number of items in the original set. How does this apply to our traveling salesman problem? Well, let's take another close look at a graph. Now, this is rather confusing, so let's take away all the lines and just arrange everything in sort of a more intuitive kind of ordering. Let's take all the calls that end at B and stick them together, all the calls that end at C and stick them together, and so on and so forth. Look at what's happening here. Essentially, with B taken, we have C and D left, and we're generating a power set out of C and D. Essentially, what we're doing is, for each city, we're generating a power set of the remaining cities. Of course, what this means is that, we're generating as many power sets as there are cities. Now, I know this is extremely simplified, but if we were to put all of this together, what we essentially get at the end of the day is n times of power sets. In other words, the number of operations we need to do here is n times 2 to the power of n. Now, let's zoom in on just one operation itself. How much work is that? You see, it needs to visit as many as every other node. Not always, just sometimes. But the point is, our upper bound will be O(n). So for this algorithm, the overall time complexity, of course, is just a multiplication of the two things we've just seen. This, at the end of the day, gives us an overall time complexity of O(n) squared by 2 to the power of n. By no means a fast algorithm, but actually faster than the factorial version. And there you have it. This is basically the last proper episode of graph theory, and hopefully, we've sort of ended it off with a bang by looking at one of the hardest problems in computer science. Now, there is actually something we haven't discussed, and that is for hard problems like the Travelling Salesman Problem, we don't always have to get, the rigorously correct solution. Instead, sometimes approximations can suffice, and these approximations can be computed much quicker and still give us an answer that, may not be perfect, but is considered not too bad. So yeah, that's another way we can actually work around the problem, by just not going for the precise, rigorous solution. Anyway, that's it. I hope this episode has been insightful. Thank you very much for watching, and until next time, you're watching 0612 TV. Thank you very much for watching. If you liked this video, consider checking out the rest of my work on my channel. Alternatively, you may want to check out a playlist of the other videos in this series. If you'd like to show me some monetary support, I am on Patreon. You can find a link to my campaign in the video description. Of course, you can simply like this video or leave a comment. I'll be sure to respond as soon as I can. To keep in touch with my future uploads, do subscribe to this channel. And for even more updates, check out the official Twitter account for this channel at 0612TV. Thank you for your support.